If you're starting to get a little bit weary of the number of sines and cosines and coefficients to keep track of, there is hope. There's a more compact form of this. So we can think of our infinite sum of sinusoids now as the sum of a DC term, or DC offset C naught, plus our sum from n equals 1 up to infinity of C. Now we're using C for this compact form as our coefficient. And then cosine n omega naught t, and now this is also including a phase shift, phi n, here as well. And if I want to think of this amplitude coefficient Cn and the phase term in terms of the coefficients that I already know, I can define Cn as an squared plus bn squared, and the square root of that. And phase, as defined here with this plus term, is going to equal the negative inverse tangent of b of n over a of n. Okay, and this is interesting because I now have these two components, c and phi, along with c naught, that are defining kind of every harmonic and the fundamental frequency components of my Fourier series. And so the C's in combination with the Phi's, I can actually plot that to give myself a visual representation of the frequency content in the signal. Okay, and I can think of these as amplitude and phase spectrum plots. And in general, we'll primarily talk about the amplitude spectrum plots. We often tend to drop phase. We assume we have, for example, an even function or an odd function, in which case the phase is constant. But if you have a more complex function, you'd absolutely need to keep the phase information in there in order to make it make sense. But let's give ourselves a quick example. So I have a y of t is going to equal 2 plus 4 cosine of 2t plus 3 sine of 4t, say. And then I can rewrite this all in terms of cosines to get that more compact form. So here y of t is going to be 2 plus 4 cosine of 2t, and then plus 3, and then I'm going to transform that sine to a cosine by adding a phase shift. Right? It keeps the same frequency, but now I am just saying my sine is going to be my cosine with a phase shift of minus pi over 2, so minus pi over 2 in here. Okay, and I can take these values and plot them, so these amplitudes, these coefficients, these C coefficients, and these phase coefficients, and plot them on an amplitude spectrum plot and a phase spectrum plot. So let's start with amplitude. So on for a spectrum plot, we're plotting frequencies. It's a little confusing to go from what you're used to plotting against time to now plotting against frequency. In a Fourier series, we have a discrete number of frequencies, right? So we're going to start with our omega naught, which in this case is going to be 2 radians per second, and we'll have 4 radians per second, and of course this is 0 radians per second here. So I'll include those ticks down on the phase spectrum plot as well. All right, and now I'm going to plot my amplitudes on the amplitude spectrum plot. Okay, so at DC or 0, I have an amplitude of 2. And so I most often draw these as a little lollipop, kind of a dot on a stick here. At a frequency of 2 radians per second, I have an amplitude of 4, and so I draw this up here like so. And then at a frequency of 4 radians per second, I have an amplitude of 3. And so I'm going to sketch this right here. Right? And most of the time, honestly, we're going to assume we already have everything in terms of cosines, and we have an even function or an odd function, and so the phases are constant. But in this case, the phases are not constant. And phase doesn't make sense at 0 radians per second. But then at 2 radians per second, I have a phase of 0. And then at 4 radians per second, I have a phase of minus pi over 2, and so it's drawn once again as that lollipop, where I have a kind of bar going to the dot here. Right, so in this case, what I have drawn for you is this is the amplitude part of my spectrum plot. So this is an amplitude spectrum plot, and then I have the phase component of this, the phase spectrum plot. And just to emphasize that this is just a new way of thinking about these signals. Instead of their value over time that you're used to thinking about signals, we're instead thinking about the frequency content of a signal. And so I can sketch that signal in time or in frequency. Frequency, I would use that amplitude and phase spectrum plot. So I'm going to start this with this sample signal right here, where I have 2 plus 4 cosine of 2t. I'm going to do my best to sketch a sinusoid for you. Okay, so I used a number of different parameters in order to sketch this sinusoid. So my omega here is 2 radians per second. This is equal to 2 pi f, which tells me that f is equal to 1 over pi hertz. And that tells me that my period is the inverse of my frequency is going to be pi seconds. And so I've sketched out my time axis in terms of pi, and I've drawn my period such that my period of the sinus of this cosine is pi. Right? I've also provided a DC offset of 2 to this, right? So the mean of this signal is 2 right now, and then the amplitude above and below that mean is 4. So I go all the way up to 6 and all the way down to minus 2. Right, so that's one way of drawing this signal versus time. The other way would be to sketch it versus frequency. And in this case, I only have 2 frequencies to worry about. I have DC, or 0 frequency content, and I have my fundamental frequency, or 2 radians per second. Right, and so at DC, at omega equals 0, I have an amplitude of 2 right here, and at 2 radians per second, I have an amplitude of 4. And my phase, this is all I have here, so my phase is constant, so I don't even need to bother with the phase spectrum plot. The amplitude spectrum plot includes all of the information I need, because this happens to be an even signal, and therefore I'm only dealing with cosines. Right, and even for a basic signal like this, that maybe I have a time plot of this, maybe I've captured this as some kind of sensor data that I've captured on my Arduino, I can still get a very basic idea of frequency content from a signal like this. It's clearly a periodic signal in this case. Right? I can look at the fundamental frequency by looking at the primary period, the period over which the signal is repeating. In that case, this is 2 pi. Is my period, and that's ultimately going to give me a fundamental frequency of 1 radian per second. Right, I can also see that there's something just beyond the basic fundamental here. I can see that I have another kind of sinusoidal component, looks like a lower amplitude component to this, and I can try to get some sense as to what harmonic that's at if I count the cycles that are in this signal. Right, so in this case, if I'm starting from here, I have 1, 2, 3, 4, 5, 6 of those extra little bumps there. I could also go in here and try to measure the period of this, but often counting those cycles is the better way to do it. So this one will have a frequency of 6 times this right here, so 6 radians per second. And then finally, I need to get some sense of what amplitudes each of these frequencies are at. So definitely I have a DC shift in this signal. I can see the average is about 2 here, so that's going to be my DC component to this signal. And I'm going to, it's going to be a rough guess, but I'm going to say I have an amplitude, if I kind of average this bottom and this top here, I'm going to have an amplitude of this primary signal, this signal that's at my fundamental frequency, omega is 1 rad per second, of 4. And then finally I need to look at an approximate amplitude for this higher frequency, this harmonic that I have in here, and I'm gonna estimate that that one is about 1 here. Right, and it is a very rough estimate. I can go in and actually do the math that we talked about and actually calculate the coefficients from this signal. But this is a fairly straightforward way to just eyeball things and get the basic principles of an estimate of the amplitudes, and they don't have to be perfect, but an estimate of the amplitudes and the frequencies. All right, and just to remind you of what we were looking at on that last plot, these were our estimates. Right, an amplitude of 4 at a frequency of 1 radian per second, and we calculated that from the fundamental period here. Then at 6 radians per second, we had an amplitude of approximately 1, and at 0 radians per second, our DC offset, we had an amplitude of 2. And so I can plot that on an amplitude spectrum plot here. So I have an amplitude of 2 at 0. At 1 radians per second, I have an amplitude of 4 here. And then at 2, 3, 4, 5, I have amplitudes of 0. And then finally at 6 radians per second, I have an amplitude of 1. Right? And once I have this amplitude spectrum plot, I can back out what this signal actually was. So I can just read my signal off of this amplitude spectrum plot. So in this case, I'm going to guess, it is an estimate, that y of t was approximately 2 plus, and then I have an amplitude of 4, cosine my omega naught is 1 t, and then plus 1 times cosine of 6t. Right? And this is my estimate for what this signal actually is, and I did that by estimating frequency content in this signal and amplitude of those respective frequencies in the signal, sketching my amplitude spectrum plot, and then pulling out the equation from there. Okay, and if we go back to this square wave example, I can actually go through the math and compute the coefficients for this. That I will leave as a wonderful exercise to the listeners here. But I can start, I can give you basically what the amplitude spectrum plot of this should look like. So I have a DC component of this of 1, and so I will have a 1 at 0 radians per second. And then at 1 radian per second, which remember is the fundamental frequency of this particular square wave, I'm going to have an amplitude of 4 pi. So all the way up here. I'm going to have nothing at 2 radians per second. Then at 3 radians per second, I'm going to have an amplitude of 4 over 3 pi. Nothing at 4 radians per second. At 5, I'm going to be 4 over 5 pi, and the scale is not perfect here. Nothing at 6 radians per second. Then 7, I'm going to have 4 over 7 pi. And this will continue getting smaller, right? The higher frequencies, I'm adding less amplitude to the signal in order to ultimately make this square wave. But this gives you some idea of what an amplitude spectrum plot for a more complex periodic signal might look like. In this case, our odd square wave here.